All right, so welcome everyone to the ninth ROS2 Hardware Acceleration Working Group meeting. Happy to have everyone in here, and hopefully we'll have a great meeting. So let's kick it off as usual. Let's start with some introductions for those of you that are new to the group and would like to say a few words. Typically, we just say hi, say who we are, of course, our organization, and then what we are working on or how it is related to hardware acceleration. So yeah, I'll just open up the mic for newcomers, please. Don't be shy.
Hi. So I'm Prateek Nagas from India. So I have a robotics consultancy called Technoyantra. So I've been working with ROS for around 5-6 years now. So we are actually now building a hardware agnostic solution for AMRs, more like an OS on top of ROS. And this is quite interesting for us because optimization of any open source software is the big challenge which many face. And of course, you can do it on a software level, but having hardware added to that will add more value. So yeah, and we just got a KV260 board. It was pretty difficult to procure one quickly, but luckily we got one. So yeah, and so we are excited to start trying out new things on it.
Thank you, and welcome, Prateek. And the good side is that there are a few folks from Xilinx in here, so if you encounter issues, you can reach them out directly. Welcome.
Yes, thank you.
All right,
Hi,
more introductions. Go ahead.
Hi, I'm Nikhil. I'm also from India, and I'm with Prateek Toyer. I work with him.
All right.
Yeah.
Thank you, Nikhil. Welcome as well.
Also, I am Bekir. I'm working on the AdWork Robotics. Someone wrote up to there, but you can write my name again, but it's not a problem. We are focused on intralogistics, especially logistic area, and I am focused on the generally navigation tools. We are working on that, and I want to participate this class, master class, or this work. Thank you.
All right, welcome. Thank you very much, Bekir, and welcome. More introductions.
So maybe I introduce myself. So I'm Tobias. I'm working at the Technical University of Munich, and we are right now working on a research vehicle for autonomous driving, and we want to add Xilinx FPGAs for our perception pipelines.
Awesome, and welcome, Tobias. Glad to have you. Anyone else? Introductions?
I'll go next. Hello, I'm Sai Charan. I'm from India, and I'm currently working as an embedded software engineer in John Deere. So we generally use FPGAs and GPUs in our work. So I'm here to explore more and contribute to the open source software.
All right. Thank you so much, Guru, and welcome.
Hi, I'm Mohammad Tahir from Pakistan. I'm currently studying bachelor's in software engineering from Rifa University, and we have final year project in self-driving vehicle. We just simulate a vehicle and using ROS1, but I'm also interested in this class. This is ROS2 latest updates, so I want to join this workshop.
All right.
Thank you.
Very welcome. Good. So we're making introductions for those of you that joined recently. So anyone new to the group, we'd appreciate if you can open up the mic and introduce yourself.
Hi, I am Mayank Sani. I am from India. So I have been working prior to Vistion Corporation, where I was using ROS1, ROS2. So I have used different version of ROS2 as well. And right now I'm working with Hair Maps, where I'm part of some autonomous driving group as well. So maybe we will be using ROS2 again. So I'm here to explore the new features of ROS2 and for networking as well.
All right, fantastic. Thank you, Mayank, and welcome.
Thank you.
I'm Peter. I'm from Denmark, and here to see what's up with ROS2. Work with ROS Run in the company I'm in.
Fantastic. Welcome, Peter.
Prashant here from India. So I'm working at Wasteful Insights. They are into pick and place waste segregation system. So I just want to check out how ROS hardware acceleration, specifically for ROS 2, will help out in optimizing the product.
Very good. Fantastic.
Hi, my name is Sagar. I'm from India. I'm working in analog devices. We just started to understand ROS. So very interested to learn something here.
Fantastic.
Thank
Welcome, Sagar. Anyone else?
Hi, I'm Rui from Portugal, Capgemini, and I'm interested in seeing how ROS2 can be used in drones and hardware acceleration for mostly computer vision.
Very well. Thank you, Rui. All right. So I think that was it. Let's go for it then. So after that short round, and anyone that's left, please interrupt me or at the end, you can also say a few words if needed, but let's kick it off. I'm now jumping into all business and administration items for the sake of time. Just a few words about the working group growth. The ROS2 hardware acceleration working group has been going on for a few months now. We started late last year organizing these meetings and hoping that we could create a community around those of you interested in hardware acceleration, so that essentially we could push some common ground for ensuring that we can speed up ROS2 computational graphs in a somewhat technology agnostic manner, so that you can, regardless of whether you're using GPUs or FPGAs, focus on your ROS code and jump from accelerator to accelerator, depending on your use case, power restrictions, and so on and so forth. For today, we had actually quite a few folks subscribed, some of which possibly will watch the session offline and afterwards. Every session is recorded, so in case you miss one or you want to go to a previous one, feel free to do so in our YouTube channel. There's a strong participation from industry, which is something that makes me pretty happy. There's big names in here that you can see from big semiconductor companies, big technology companies, system integrators, as well as big technology makers. So super, super happy. And this is, by the way, not a complete list, of course. There's many more, all of them which are relevant. There are also quite a few of you coming from academia, from small and big universities. Everyone's welcome. So that is also something pretty nice, which shows, I think, the traction that we've been creating. To give you some additional numbers, the posts we are launching in social media, and to the extent of what we track, because we don't track everything, generated the last 30 days more than 100,000 views and many, many reactions across social media channels. We have more than 2,000 video impressions in YouTube over the last, I think we're 28 days or something like that. And more than 1,000 visitors on this particular repository. I just picked one of the ones that we are contributing within the ROS Acceleration organization, where you can see everything open source and disclosed with a commercially friendly license, Apache 2 typically. So one of them is the Acceleration Examples, which is a repo that puts together blueprints for you all to build your own accelerated applications, your own sped up or faster computational graphs or computational nodes using ROS. So here you've got the sources and a description of every single one of them. And again, I wasn't expecting this, but there seems to be a significant amount of visitors and reactions. So looking forward to see where this brings us and for future growth. Now, looking at the numbers, certainly one asks, in this case, myself, what can we do better? And in this case, there's two things where definitely I'd like to bring your attention and if possible, maybe some contributions. The first one is contributions. We definitely need a bit more of activity in terms of code contribution. So maybe people working in this direction contributing a few examples back to the acceleration examples, or maybe some people is creating their own acceleration firmware layers to enable new boards. There is an ongoing activity that is being pushed by a group of individuals actually bringing the architecture to the Ultra 96 V2 from AVNet. So things like those and a few more that I'm aware would definitely be encouraged to be brought to the group so that we can discuss it a bit more, and also so that more people can benefit from that. And definitely also a bit more of industry engagement and case studies. This is something that I'm particularly keen on as more and more people start using the tools we are generating and the utilities. I definitely would be very interested to hear opinions, views, reviews, criticisms, especially from those ones trying to bring real stuff, real robots into the market. We're having guest speakers. We'll have one later on within the session today, which I'm very excited about. Typically that's going to continue, but within those sections, I would love to get maybe some industry players speaking about how hardware acceleration actually plays out in real case studies and in real problems beyond the ones we're putting together in these examples. On that, I just wanted to mention, and this is probably interesting to highlight right now, there's a new organization sponsoring the working group, which is Acceleration Robotics. And this firm essentially is focused on trying to bring up, in a very similar manner to the group, accelerators based on ROS in a somewhat accelerator agnostic manner. It is the organization that's sponsoring me right now. And for those of you working for other organizations, there are opportunities to sponsor the group and highlight some of your work further. So if you would like to take a more active participation, reach out to me and we'll look into possibilities there. So that is for what concerns the working group growth. Let's look at the second administrative or all business item, which is the robotic processing unit, which is a project we kick off a few meetings ago. Unfortunately, there hasn't been lots of progress over the last month. I've been very, very focused on the Humble release, which we will discuss just in a bit. The ROS2 Humble, HAWG, which is the latest ROS2, and the essentially the LTS, the long-term support version of ROS2, which is going to be supported for 5 years. So those of you working across industry or academia, definitely recommended to check out Humble for new projects. So essentially, I've been super focused on this and bringing things up, and I haven't had the time to take a look at contributions as well as to contribute myself on this. So pushing this out to later meetings. Again, the ticket is out there, so anyone interested in this particular sub-project can go to that and comment or contribute. Jumping into progress review and new business, I'll touch into two topics. Actually, sorry, choosing to one with different subtopics. The first subtopic is the Rep 2000. So in particular, I'm just going to touch on the new launch highlights, on Humble's highlights. The first highlight and one of the interesting things and capabilities that we have hardware acceleration-wise in ROS2 Humble is the fact that there's been a push specifically from my group side to try to bring hardware acceleration support while also integration with custom production-grade operating systems. So in particular, for those of you familiar with REPs or ROS enhancement proposals, these are kind of like community conventions or community standards from a ROS perspective, which try to standardize how things should be done in the ROS community. Rep 2000 speaks about ROS2 releases and targeted platforms. If we take a look at the one that is supposed to be for Humble, for the new release, we can see here in this last column that OpenEmbedded was targeted. Unfortunately, there's been some glitches in terms of support for MetaROS, which is the project that groups together the Yocto recipes for enabling ROS in OpenEmbedded/Yocto based constructs and projects. So we took on that essentially work. And for the last month, I've been pretty, I would say, intensively working on ensuring that we had enough capabilities to bring a preliminary level of support to Yocto with Humble. The contributions of this, I think, have been pushed to the MetaROS repo, particularly, and you can check this out, there's still an open pull request in here. And just by looking at it, you can see how essentially, more than 1,000 files were modified and more than 60,000 lines of code were changed. So it's a significant amount of changes within this repository. As I said, it was lots of work, lots of changes. Humble introduced certain modifications from a recipe perspective, but particularly the big leap came while supporting Honister, which is a release of Yocto we were targeting in this case. Many of the files were fortunately modified in a somewhat pseudo-automatic manner by using some scripting. However, many others had to be manually modified. So if any of you is looking into building production-grade robots using Yocto, you may want to check this out. Right now, there's preliminary support tested with certain boards that I will discuss just right now. Of course, this is by no means final. It's still under review, and everyone's welcome to contribute. Actually, I want to highlight that since Humble is possibly the recipes of Humble need to be updated, because this was worked out for the Humble launch. But then soon after that, there should have been a new release from the build farm coming out of Open Robotics. That's my understanding, at least. And that possibly just modified some of the hashes of the packages, which possibly will lead to some changes in the recipes. So if any of you has bandwidth, it's super encouraged to contribute to this, of course. Because you will get familiar with possibly one of the really relevant pieces of how to bring ROS to Humble to production-grade environments. And also because there is lots of overlap of customization of software and customization of hardware when it comes to hardware acceleration. So encouraging everyone to have a look at this. As I was saying, we've brought support for certain boards and their corresponding BSPs, some which are officially supported by the manufacturer, some others which aren't. So in the case of AMD, there are a few boards which were tested against the official BSP from the manufacturer. In some other cases, it was tested against community contributions, community BSPs, but regardless, the capabilities were tested and led to root file systems which included ROS to Humble with fully fledged capabilities and based on Yocto. So yeah, that is that. This is closed right now, but anyhow, it was an interesting effort that led to some interesting results. For each one of these boards, you have a write-up that we made at Acceleration Robotics that explains the rationale, why this is important, some of the actual features that you get by building your own Linux distribution, and then I walk through on how to do it step by step. Again, it's not bulletproof because of the fact that some recipes may change. So if anyone has some bandwidth, contributions are super welcome. Now, Rep 2000, and in particular, the enablement of Yocto based flows or OpenEmbedded ones is certainly one of the big highlights hardware acceleration wise that I think we can claim for what concerns Humble. The second one is Rep 2007. Claimed as type adaptation, which in a nutshell is an extension of the ROS client library for C++ that will make it easier to convert between essentially ROS types and custom user-defined types for topics, services, actions, and other things in a nutshell. Let me bring this again, which moved. So Rep 2007 was pushed by Open Robotics. You can check it out online in here. There are some examples, and also Open Robotics released some examples in their corresponding repositories, which show you how to use it and how to leverage it. Type adaptation in a nutshell allows to build computational nodes that are somewhat agnostic to whatever types are used within the accelerator and make lives of developers easier. So encouraging everyone to check this out. Definitely one of the blueprints of what we are building in here, hardware acceleration wise. The third item I wanted to highlight, which is unfortunately still being reviewed as a pull request, but we have discussed this in the past meetings, is Rep 2008, which is the ROS2 hardware acceleration architecture and conventions. This ROS enhancement proposal aims to bring together all of the other aspects and reps so that we have a consistent way of understanding how hardware acceleration works in the ROS2 world. So you can expect that this rep will grow, will improve, and will enhance over time, possibly including and pointing towards other reps, such as Rep 2000 or Rep 2007 that we just discussed. Again, we discussed this in the past, so I will not stop too much in here. But in a nutshell, it from a developer's perspective, it explains how essentially building accelerators should happen in a somewhat simplified manner, a ROS2-centric way, while at the same time for silicon vendors, it provides a recipe on how to attach themselves to the ROS2 ecosystem so that they are consistent, interoperable, and don't break up this assumption of trying to be agnostic from an accelerator perspective, so that developers can jump from one accelerator to another without having to reinvent the wheel, which is at the end of the day, I think what we want to deliver for our ROS users and what everyone wants to use to avoid lockdowns. The last one, which was recently displayed, though frankly speaking, it's been contributed since I think a few months ago, at least a pull request date from a few months ago, is type negotiation, which in a nutshell is a set of classes for ROS2 that will make it possible to negotiate message types, used by publishers and subscriptions. This is a super cool feature that tackles, I think, one of the big issues for what concerns the current ROS2, which is CPU-centric. Most computational graphs are very CPU-centric, and breaking that assumption and bringing it to a more GPU or FPGA-friendly environment require you to essentially play around with shared memory or use some special constructs leveraging AXI4 interfaces. So I think type negotiation plays an interesting tune because it proposes an abstraction layer that lives at the top and which simplifies how this can be digested from a ROS2 user's perspective. We'll touch on Rep 2009 and also on the rest of them in more detail in the next meeting, because I was actually asked repeatedly to speak about this. So we'll book plenty of time to touch on this in the next session. But for now, I think it's important to highlight these are some of the, I think, important highlights hardware acceleration-wise that ROS2 Humble brings in. Of course, ROS2 Humble brings together many more things from many contributors. I encourage you to go and check the release notes. But very excited about how this is shaping up and how many capabilities we have built over the last year contributing to this group. Connected to these enhancements, and specifically connected to Rep 2008, which, as I said, it touches on trying to standardize some of the flows and conventions to use hardware acceleration to simplify things from a user's perspective. One of the topics we've been discussing historically and repeatedly is benchmarking. Benchmarking in the sense of ensuring that we do know what is our CPU baseline from a computational perspective, as well as comparing fairly against accelerated versions of that, and also comparing different accelerators, possibly coming from different silicon vendors, so that we pick what's best for our use case, both from essentially latency perspective, as well as from a power perspective and performance perspective. So on that, I'm super happy to have with us today Christophe. Christophe is I don't know if I should say a long-term contributor to the ROS2 ecosystem, but at least he's been around for quite a few years now, making really nice contributions in various directions. The reason why I'm so excited is because when you work with hardware acceleration, you do realize that benchmarking and essentially getting clarity on what you're doing is instrumental for the development of accelerators. And often benchmarking becomes pretty tricky in the ROS2 ecosystem because different groups and different ROS2 stacks are using different mechanisms for instrumenting the code and benchmarking stuff. So the exciting thing about essentially what Christophe will tell us about is that they've been walking towards a direction that's been set, I think, for the last, I would say, quite a few years, since ROSCON 2016 or something like that, where I think Ingo first spoke about LTTNG. So yeah, they've been using the Linux tracing toolkit, proposing tools on top to facilitate its use. And now he's tackling, I think, one of the really nice issues, which is once you have instrumentation and you can fetch the data, then how do you map all of that static data to the actual computational graph, right? And how do you visualize and introspect it to make sense out of what you want to optimize? And anyone that, like me, has been creating accelerators for the last year would definitely resonate with these words, because one thing is getting the performance up, another thing is essentially making sense of that in correspondence with the computational graph. So Christophe, I don't know if I'm saying maybe too much and you will tell us less out of that. I hope not. But anyhow, super happy to introduce Christophe and his speech about his paper message flow analysis with complex causal links for distributed ROS2 systems. So Christophe, the stage is yours. And again, kudos to have you here.
Thank you for the introduction. I will just share my screen. Can you see it? And can you hear me correctly, or is it too low? Or
we can hear you and we can see the screen. Seems perfect.
All right. All right. So as Victor said, I'm presenting basically the work that went into the paper, which we recently released. So this is work I did as part of my master's, and I'm currently working at Apex AI doing this kind of work. So here's a summary of my presentation. I will start with a short introduction, then talk about tracing just a little bit, just to make sure we're on the same page. Then I will quickly introduce ROS2 tracing and talk about tracing ROS2 itself. Then I will move on to the main part of the presentation, which is the message flow analysis. And then I will quickly talk about the executor and talk about the runtime overhead of this method, and then I will conclude. So if there is any questions, I will look at the chat just in case. Otherwise, I will keep going and we can answer questions at the end. So of course, in robotics, we have many different types of applications. We have safety critical applications. They can be distributed and connected over a network. And the key elements here is that for systems like ROS, they use publish subscribe patterns. So they're quite modular, and higher level scheduling of tasks is quite challenging. And of course, the systems, we often want them to hit certain performance targets, and they can have also performance constraints. And so to do this, we need debugging tools. So we often debug simply with GDB, or we use sometimes LAG, which are usually human readable strings, so quite simple. It works, but it's quite rudimentary. So for distributed systems, then you wonder how do you analyze a distributed system as a whole. So there's also some real-time constraints, and you want to try to use this in production because there's some, otherwise you can hit some quite serious problems. So especially when you try to extract timing-related data, if you influence or affect the application, then you might get totally wrong results. So you need a great tool for this. So this leads us to tracing. So the tracing is really the best tool, I think, for this. So it allows us to extract runtime execution information, which is usually low-level information. So not human readable strings. It's usually raw or binary data like integers, arrays, and sometimes strings. But it's usually data that is not meant to be read by humans right away. So it's quite useful when issues are hard to reproduce. So you can usually trace for some time or all the time. And then when you hit an issue, you can just look at the trace and start debugging, pretty much. Of course, as I said, we want to use this in production sometime, or use this to get valuable data. So of course, you want to minimize the overhead. So for this, we've been using LTTNG, which is a high performance and overhead tracer. So the usual workflow with this, the main workflow is you add trace points into your applications, then you configure a tracer, you run the application, and then this generates trace data, and then after the fact, usually you analyze the trace data. And so ROS2 tracing is a collection of tracing instrumentation and tools that's closely integrated into ROS2. So it has tools to instrument the core of ROS2 with LTTNG, again, and it has tools also to configure tracing with LTTNG. And there's a paper if you want to look at it. So I will also have a link at the end. And so the main way to configure tracing using the ROS2 ecosystem is using a trace action for launch. So you can just simply include it into your launch file, and then it will start tracing when you launch it, and then it will start tracing at the end. So it's really pretty useful when we have a complex system with multiple nodes. So you can also use it in XML and YAML files, of course, if you use those. So as for the instrumentation, we wanted to extract information about all the layers of ROS2 and know about the interaction between them. But the layers make it hard to get the full picture, so we need to gather small bits of information here and there. So this is usually the case with tracing, but it's especially the case with ROS2 given all of its layers. And then we analyze this data externally at the end, usually offline. Okay, so again, it applies to all layers of ROS2 from RCL-CPP down to the DDS implementation. So it allows us to get data about the objects, so the nodes, the publishers, the subscriptions, the timers, and also the specific events. So callback executions for subscriptions and timers, and also message publications, message takes, when messages are taken from the middleware to be executed, to be given to callbacks pretty much. And we can also extract information about the executor to get information about its states or time. And we can also, there's other information, but for this presentation, these are the main data points. And so we use this quite raw data, and we need to analyze it. So to process it, I've been using a Trace Compass, which is a trace data analysis framework, and it also has built-in analysis. So you can use it with your traces to get data, usually with the Linux kernel, but also it can also take in other trace formats. And you can also develop your own analysis for the Trace Compass. In the specific, one important thing we need to keep in mind with distributed systems is that we of course need to combine traces from all the systems. So usually after execution, you can synchronize the systems beforehand using NTP or PTP, or you can also synchronize the traces afterwards using Trace Compass. And then you can, in Trace Compass, we model the ROS2 objects in the instances using the trace data. And since we wanted this to work with distributed systems, there's some things to keep in mind. So the trace points, they use pointers as unique IDs usually to simplify payloads. So those pointers are, of course, memory addresses. So for it to be valid across multiple processes, then we need to combine it with the PIDs. Then for this to be valid across multiple systems in a distributed system, then we need to combine it with the host, specific host ID, which is implementation defined. And then we can use this pre-processed data, which is higher level than the raw data from the trace, and then we can build analysis or extract metrics quite easily. So this leads us into the main part of the presentation, which is the message flow. So the message flow is a graph of the path of the message across the distributed ROS system. So if you think of the ROS 1 or 2 computation graph as a directed acyclic graph, then it's from usually the root of the graph to a leaf of the graph. So from message to node, then another message, and so on. I built a first prototype of this for ROS 1 back in 2019, if you want to look at it. I have a blog post, but it had several limitations. It was really a first prototype, pretty basic. One limitation was that the tracking for messages across systems was quite unreliable. It was working, but was not really reliable for multiple messages. And it also only considered direct one-to-one links between messages, meaning that for one input message into a node, it only considered one output message. So this was limiting, and it didn't really apply to most real use cases. So this is why this new paper is really an improvement on this. So yeah, so this message flow analysis now is again the same thing, but applied to a distributed ROS2 system. And to build this, we need to combine multiple segment and links. So the one segment we need to get is a subscription timer and callbacks. So for example, this one, and then the following segments after this are usually message publication instances. So in this case, these messages were published during the timer callback. Then the next segment would be, in this case, for example, here, transports links, so over the network. And then, so in this case, for example, this message went over the network, then was received, and then the callback was executed. Then during the callback, a message was published, and so on. So the graph continues. And we also have causal message links, which I will explain shortly. So they're just the link between input messages again and output messages. So this is really a simplified representation of the message flow graph. So the first link to consider is a transport link. So it is the link between a publication instance and the corresponding subscription callback. So in this example, we have two systems. So the first system below and then another system above in this representation. This is from the resulting trace compass output pretty much. So one system here and then the other system there. So the first system has a periodic timer, so 5 milliseconds, and during its callback, it just publishes a message on topic A, so like here. And then this message is sent over the network to the subscription on the other computer. So then it's received, and the callback gets executed. So the transport link is really this arrow right here. So it should be noted that it includes more than just network time. So in this case, it's network time plus the time delay between the reception by the actual malware and the actual callback execution. So there should be, if we improve this method, we would add some additional segment right here before the callback execution. And by definition, this link is really a one-to-many link. So a message is published once, but it can be received by any number of subscriptions. So this is important to keep in mind. So this is already an improvement on the previous method. So then we'll talk about causal message links. So it is the link again between input messages and output messages, and it can be, of course, many-to-many. So when a message is received by a subscription, something happens, and it leads to some output messages that are published by a publisher. And we define here the causality between those messages primarily on message data. So the data of an input message is used to generate the data of an output message. So this is strictly this, without any strict constraint on time. So it can be directly related time-wise, or it can be really indirect, which explains pretty much the rest of this presentation. So for example, here, direct links between messages, there's one here, so in red. So this the message for this subscription callback directly led to this output message that was published. So this is a direct causal link. But we also have, again in red, these indirect causal links. So in this case, this message was received, and eventually it was used to publish a message later during this timer callback here. And same thing here. This message was received here, and eventually was used to publish this message at the end. So it can be direct or indirect. And so for direct causal links, as I said, it's in this case it's really inside the subscription callbacks. So message publication happens in this case, for example, here inside the subscription callback. So it can be pretty easily inferred. So we don't need any additional information or instrumentation. So the instrumentation tells us that the callback started at some point and then ended at some point, so that if a publication happens on the same thread within those time points, then we can infer that the messages are linked. So that's pretty easy to do. And now the more complex cases are for the indirect causal links. So the unknown here is that user level call is difficult to include in the execution model. So it's difficult to model. So this is usually done above the ROS2 API, so user level. For example, people often use in real applications message caches, it can be as easy as just a message that you copy into a cache, or you just keep a message pointer or something like that. So it's hard to keep track of those messages. So as I said, it leads to indirect causal links, which are asynchronous. So again, there is no direct time link, and they are again many-to-many links. And this kind of link requires additional user level information, which we collect using simple trace points. So for inside nodes, user or simply have to give the type of link that they are using, give all the input subscriptions and the output publishers, and then we just infer the rest using this information. And we can include this inside the preprocessed model of objects and instances. So that's pretty much it. We'll talk about, I will show 2 examples that we define, 2 indirect causal links that we define, but we could add more afterwards. So the first one is what I call the periodic asynchronous link. So messages are received and then cached. So for example, here, this is the node with the special link, and it receives messages from 2 nodes on topic A here and topic B. So the first message is published and then received by the special node. So it's just the subscription callback is quite short, but the message is simply put into a cache. Then same thing happens for topic B. So the message is received and it is put into a cache. And then periodically a timer gets called, and it takes the messages in the caches and then computes the result and publishes the result inside a message. So the input messages then should be linked to this output message through an indirect causal link. So this is what you see in red here. So the timer callback published a message, but this message is linked to the received messages that were received beforehand. So I hope this is clear enough. So then the second link is quite similar. It's the partial synchronous link. So again, messages are received and cached. But in this case, messages are published. They may be published inside the timer, the subscription callback directly. So for example, here, a message is received from topic B, and then a message is received from topic A. And in this case, since cache for a message from topic B was available inside the cache, and a message from topic A was available since this is the subscription callback for the message on topic A, then the output message can be computed and published. So then this message is linked asynchronously to the output message, but the message from topic A is linked simply directly to the output message. So this is why I called it a partial synchronous link. So again, these are 2 simple links that we define and model using by looking at existing systems, but we could add define other links if there are like if you have other special links in your system, you can add them to this model. And so the result of all of this information put together is the message flow graph. So for example, here I took the AutoWare reference system, which is a system that is based on the AutoWare computation graph, and I split it up over multiple processes. So there's a lot of nodes. So I put them over multiple processes, and then I split those processes over 2 hosts. So you can see here that we have 1 host and then another here below, and then split over multiple processes. So you see all the PIDs over here. And so I simply selected 1 root message. So in this case, a message from the front Lighthouse driver. And then the message flow graph was computed using this input information. And so it goes pretty much through the computation graph, and it results at the end in actually 3 output. Basically, in this case, they are command for the drive-by-wire system, the vehicle. So in this case, it leads to 3 separate output messages, but they are they could be loosely related to the initial message, since they can be asynchronous and quite indirect. And so using this visualization, we can extract end-to-end latencies, like for example, from this point to one of the output messages, and we can also, of course, extract intermediate latencies, so callbacks or network latencies and so on. And this allows us to visually understand the execution and find bottlenecks. So the goal here is really to compare this information with other execution data. For example, with the Linux kernel, we can have scheduling information, I/O, and so on. And we could also compare this to other application data. And this is why really we use Trace Compass. It's the other analyses can be quite easily compared to this output here. And now a short section on the executor. So you'll see why it's related quite soon. The executor, of course, is a high-level task scheduler. So it fetches new messages from the middleware and then calls your user-provided callbacks with those messages. And it also executes timer callbacks and so on. And the challenge with the executor is that it does scheduling on top of the OS scheduler, which can sometimes be inefficient and non-deterministic. So there's a lot of work on this that's been done in the past few years. There's many solutions depending on your application and requirements. You could use other executor designs that are better suited to your application. You can optimize scheduling policies and priorities. And of course, you want to study and compare executor designs and optimize overall application performance, which applies, of course, to hardware acceleration. So we built a view of the executor state over time. So the main states are either executing, so executing a timer callback or a subscription callback, or waiting for new messages or for timer trigger. So in this case, green is executing, and orange is just waiting for something. So you can see that some executor instances are busier than others. So for example, in this, the first system above is quite not really busy. It's mostly waiting. But the system below is some processes are busier than the other half. So this can cause message processing delays and bottlenecks. So in this case, we can, for example, we had a PID. It's not the same PIDs, but oh well. Oh yeah, so it's not another experiment run, so it's different PIDs. But in this case, we took one process. So in this case, 690, and we used instead of using a single-threaded executor, we used a multi-threaded executor with 2 threads. So it, of course, it spreads the load over 2 threads. So in this case, it's less busy, and it can execute receive message callbacks for received messages more quickly. So we can take a look at the results on the computation, the message flow. So for example, here we have 3 nodes on the same process, so 690 again, and these 2 nodes, so in here, Ray ground filter and voxel grid downsempler here, they receive the same message, and they have to execute callbacks. And with, of course, with a single-threaded executor, they would execute callbacks one after the other. But in this case, using the multi-threaded executor, they can execute the callbacks concurrently. So then the end-to-end latency is shortened. So this is quite a simple example, and of course you would want to look at more complex executor, but this is just a simple illustration of the method. So if we talk about runtime overhead, if we extrapolate from previous overhead results, so from LTTNG and from ROS tracing, it should be, we expect this to be very small. So we executed a pipeline of nodes, first without tracing and then with tracing, which has a total end-to-end latency of about 260 milliseconds. And then we just took the difference in the end-to-end latency, and it's about like less than 0.06%. So it's quite small. So I think it's quite good for our applications. And of course, it's likely challenging to measure on more complex systems. I spend a lot of time measuring this kind of data So if you measure end-to-end latency for distributed systems, you hit all of the jitter and all of the variation, scheduling, and I/O, and kernel, and everything. So it's pretty challenging to measure, since the overhead is quite small. So in conclusion, we can track messages across nodes and hosts, and then we use this information to build a message flow graph. And then for some of the information, we need to use user level annotation to find the more complex indirect causal links. We can use this information to compute end-to-end latencies and intermediate latencies. And we can use this method to study and improve performance for ROS2 applications. And I have some notes for future work if you're interested, but I would invite you to read the paper if you're interested, since we are a bit short of time. So again, this is the paper I presented, and there's a QR code on the left above, and then for the ROS tracing paper is also available. So yeah, questions?
Thank you so much, Christophe. That was fantastic. Folks, let's ask Christophe whatever you think you should. Right now, maybe I can kick it off with maybe 1-2 quick ones. The first is, so I would love to pick your brain, Christophe, about essentially the ongoing activity you guys, and particularly you, have been leading in using LTTNG and these open source tools, including Trace Compass, and the proposal of ROS2 tracing, which build on top of LTTNG. I'd like to know how do you see the future growth of those tools for what concerns hardware acceleration? Because we are seeing some ongoing friction with some proprietary tools, like, for example, AMD has its own proprietary tools to have introspection into the kernel interactions with the PS, with the processing systems. NVIDIA have their own tools for also doing GPU introspection. So how do you see the landscape in here? Do you see those tools, which are proprietary, being used for data specifically, or do you see more everything converging towards this kind of like vendor-neutral approach by obviously extending it with visibility towards those other processing units?
Well, I don't know much about like vendor-specific tools, like from AMD or Xilinx or NVIDIA. But yeah, that's a good question. I know that so other people in my research lab, they work with AMD and so on GPUs and FPGAs, and they, from what I understand, they just use the vendor-provided tools. There's a pretty easy like conversion between the information they can extract from those tools and like information that LTTNG generates. But so you can pretty much easily use those tools and then generate the CTF information, so trace data, and use the same analysis tools, such as the one I presented. But yeah, I don't really have an easy answer for you.
No problem. And I would be interested if we can follow up. If you can give me a pointer to actually those things you guys are using, because so I am aware there are some like utilities to convert formats. But the main friction I've been finding is not so much about getting things consistently into CTF format. It's more about getting the clocks actually right and making them make sense, because you may get actually things somehow data consistent. However, if you don't have time consistency across, let's say, your CPUs and your GPUs, then that's where the fun stuff starts happening. So so I would follow up with you. Maybe I can get a pointer to those things. Cool. All right. More questions?
So there's this question about repeated messages. So if you use it, for the two cases I presented, so for the two indirect causal links I presented, if the same message gets reused for two output messages, it will be supported quite easily. So, but if you have something else, then we would need to take a look, but yeah.
Okay. So Kunal is asking a couple of questions. The first one is if we can add metadata to the tracing data, and well, that's a pretty easy one. Christophe?
Yeah, you can just add your own trace points into your own applications. So that's easy to do.
Yep. And then the second one asks, yeah, sorry, go ahead.
Network overhead for tracing, it's not related. So unless I'm missing the question, I'm not sure what you're asking.
Kunal, would you like to elaborate?
It's strictly CPU overhead or latency overhead. So
yeah, so maybe I can add.
No, okay, so for most cases, the traces are generated and written to disk on the system itself. They can be sent over the network, but in most cases, it's done directly in the system itself.
Yeah, and just to clarify on that, so essentially, Kunal, yeah, exactly. You essentially get them into each one of your systems, and then you pack them together however you wish to analyze. But yeah, that's a post process. You don't need to do that online. So but maybe on this,
yeah, sorry. It might be worth looking at. So of course, writing the trace data to disk is also an overhead. So sometimes it's less of an overhead to send the data directly over the network for another system to basically ingest. But in most cases, it's simpler to just write it on each system.
That's actually a great point, and I had not think about that, comparing the I/O overhead versus the network one. And I don't think there is. Have you guys done anything on that?
I haven't never tried it, but I know LTTNG support this kind of workflow.
Cool. Well, that's definitely an avenue for further research. Those of you interested on this topic. All right, cool. So awesome. So I think we reached the top of the hour. Unless there are any other questions, we will thank Christophe. It was fantastic to have you. Kudos again for the paper. Actually, the papers, I should say, because I think you guys published a couple. I saw a second one touching on the perception analysis. So that's
specifically applied to SLAM systems.
Yeah, super nice. Definitely recommended everyone to take a look at that. And as I said at the beginning, this is a super exciting topic. I've been following Christophe's work for quite a while now. I personally believe that hardware acceleration definitely demands, let's say, a tracing and benchmarking centric approach. A, to further optimize the accelerators, and B, also to have always graph-centric view, so that you don't essentially damage parts of your graph that you do not necessarily want to do. The complexity, though, blows up at the moment you start seeing the tracing information. And Christophe today just presented a super nice set of contributions that essentially do much of the work for you, digesting it, proposing some data structures, and then presenting it nicely for visualization. So yeah, again, kudos, Christophe. Thank you again for your time. And to everyone, we will have one more session before the summer break next month, by the end of June. And the announcement will come up soon in this course. Next session actually is going to touch in more detail some of these unique new capabilities that ROS 2 Humble brings in from a hardware acceleration perspective. We'll have a session discussing particularly a framework for facilitating hardware acceleration. So definitely encouraging everyone to check that out. It's going to be, again, the last session before we break for the summer. And after that, we will re-engage in September with more exciting stuff. Thank you, everyone, for joining. Thank you, Christophe, once again. And to everyone, have a fantastic rest of your day. Ciao, ciao. Take care. Bye, everyone.